In a high-stakes enterprise environment, the moment a primary fiber link snaps into darkness, the network enters a state of critical transition. Link failures are an inevitable reality of physical infrastructure. Because hardware will eventually fail, the failover architecture serves as the primary determinant of overall network reliability. Quality of service, or QoS, functions as a strict, quantifiable baseline for evaluating network health during these events. We measure the impact of a failover using 4 specific telemetry metrics: convergence time, packet loss, latency, and jitter. The choice of interior routing protocol dictates the severity of performance degradation during an outage and how effectively the network returns to a stable operational range. To evaluate these performance swings, we must compare the 2 most common interior protocols, EIGRP and OSPF, within modern IPv6 topologies. Empirical simulations reveal measurable performance gaps between EIGRP and OSPF during a primary link failure. Our analysis will follow the telemetry, beginning with raw simulation data, deconstructing the internal protocol algorithms, and finally integrating them with BGP for external routing policy. Engineering a resilient network requires a reliance on the empirical mathematics of failover rather than the claims found in vendor marketing. Data from a recent MDPI testbed provides the baseline. This study utilized an IPv6 environment in a dual ISP failover configuration to isolate the behavior of each protocol. The structural layout involves 13 Cisco routers, divided to support both an overlay and an underlay network. Internal data traffic is assigned to tunnels 1 and 2 in the overlay network, while external internet traffic is routed through the underlay via ISP-A and ISP-B. This chart displays the unauthenticated convergence times. In this environment, EIGRP established an alternate PANOP with an average recovery time of 134.2 seconds. Under identical failure conditions, OSPF averaged a slower recovery time of 159.1 seconds. Moving to data integrity, this line graph plots the percentage of packet loss occurring throughout the failure event. The simulation recorded EIGRP restricting packet loss to 5%. OSPF allowed a higher loss rate, dropping 5.4% of traffic before the network stabilized. While baseline latency and jitter were comparable, the introduction of authentication overhead demonstrably worsened both metrics across the board for both protocols. The data establishes a clear performance advantage for EIGRP. Understanding this disparity requires an investigation into the algorithmic logic driving each protocol's reaction to a link failure. We begin with the computational mechanics of the Open Shortest Path First, or OSPF, protocol. OSPF identifies a link failure when it stops receiving hello packets from a neighboring router. Once a failure is confirmed, the detecting router immediately generates a Link State Advertisement, or LSA. This initiates LSA flooding. Every router within the area must receive the advertisement, acknowledge the change, and synchronize its internal database to reflect the new topology. Only after synchronization is complete does the protocol calculate the new optimal route using the shortest path first, or SPF, algorithm. The SPF process is computationally expensive. The router must recalculate the entire network tree from its own perspective to find the new shortest path. This requirement for network-wide flooding, followed by intense CPU recalculation, creates the recovery delay observed in the OSPF telemetry. EIGRP utilizes a fundamentally different approach to routing updates. The Diffusing Update Algorithm, or DUAL, acts as the primary engine for EIGRP's path selection. DUAL calculates the primary path to a destination, known as the successor route, and installs it into the routing table. EIGRP's significant advantage is that DUAL pre-computes a loop-free backup path, a feasible successor, and stores it passively in the topology table before a failure even occurs. This pre-computation alters the router's reaction at the exact moment it detects a primary link failure. EIGRP avoids a network-wide recalculation. It immediately promotes the pre-computed feasible successor into the routing table to restore connectivity. This pre-computation mechanic is the direct cause of the lower convergence times and reduced packet loss documented in the MDPI study. Interior routing speed is only one component of a resilient architecture. Interior protocols like EIGRP and OSPF cannot manage failure across different autonomous systems or the internet backbone. External traffic requires the Border Gateway Protocol, or BGP. BGP functions as a deterministic policy engine that selects paths based on specific attributes, rather than simple link metrics. BGP determines the optimal path for external traffic by following a strict 11-step selection algorithm. Step 1 evaluates the weight attribute. This Cisco-specific value allows an architect to force a local routing choice on a single router. Step 2 evaluates local preference, which communicates outbound routing policies to every BGP router within the autonomous system. By manipulating these two attributes, architects can ensure that ISP-A serves as the primary exit point, while ISP-B remains as a load-sharing backup. Comprehensive QoS requires layering the recovery speed of the interior protocol with the deterministic policy enforcement of BGP. A fully realized dual ISP architecture requires all three protocols to function in unison. Upon detecting a primary link failure, the layered architecture automates the diversion of traffic to secondary links to restore connectivity. Each protocol serves a mechanical role. EIGRP uses precomputation to reduce recovery time. OSPF uses recalculation for a synchronized map, and BGP enforces external policy. For enterprise environments prioritizing faster recovery times and reduced packet loss, the simulation data gives EIGRP a measurable mathematical advantage. OSPF remains the choice for multi-vendor environments due to its status as an open standard protocol compatible with a wide range of hardware. Regardless of the interior protocol, architects must use BGP attribute manipulation at the network edge to prevent routing loops during interdomain transitions. Achieving true IPv6 network resilience requires deliberate, empirically driven algorithmic engineering rather than a reliance on physical topology alone.